In today's tutorial, we are going to look at some of the applications of eigenvalues and eigenvectors. That's the point of today's tutorial. Basically, the questions are going to come from the section on matrices, and we're going to look at two nice applications of eigenvectors and eigenvalues. We're going to do two questions. 92 is the first one, and 93 is the second one. So the first one is on so-called quadratic or quadric forms. So on to the first one. There's a number of parts to this question, all based around this matrix A. Now notice that the matrix is what we call a symmetric matrix. Okay? It's symmetric because if you draw some sort of line down the diagonal, the principal diagonal, there's symmetry in the principal diagonal. Okay, so what I've done is I've pre-prepared some of the solutions because there's a few parts to the question, right? And in fact, there's a few things like row reduction and a few calculations put in. So usually I don't pre-prepare the questions, I do them live. But today's a special tutorial because there's lots of calculations involved. So I want to get through two questions rather than just one. Okay? All right, firstly we're asked to show that the eigenvalues of the matrix A are 1, -1, and 3, and find the associated eigenvectors. Hence, express this equation here in terms of these principal axes, big X, big Y, and big Z. Now, why would you want to do that? Well, it's not quite clear what type of curve this is. But if I can simplify it in terms of these so-called principal axes, big X, big Y, and big Z, then hopefully I can get some idea. So think of this big X, big Y, big Z as a new coordinate system, somehow related to little x, little y, and little z. Secondly, we're asked to write out an orthogonal matrix P such that little x, little y, and little z is the transform of big X, big Y, big Z under P. And part C asks you about the shortest distance from the surface to the origin. So you don't have to write all of this down, of course, but I want to explain as I go through. So A is a symmetric matrix. Symmetric matrices are nice because we have this principal axes theorem that we can apply to it. The first thing is that I'm going to claim that the eigenvalues are 1, 3, and 4? Yes, 1, 3, and -4, sorry. So the equation that we solve is just the following. We look at the determinant of the matrix A minus lambda I, where I is the identity matrix. And we want to solve this equation here for the lambda. Okay, so we can think of any value lambda that satisfies this particular determinant equation. That's going to be an eigenvalue of A. Okay? Just some real, in this case, it's going to be a real number. It could be complex, but the one thing is it's certainly not a vector. Okay, so let's work out A minus lambda I. Well, it's just this matrix with, a minus lambda there, a minus lambda there, and a minus lambda there. So look at the diagonal and just replace that. Okay, so I'm interested in the determinant. So how do I expand or calculate this determinant? Well, you can do it a number of ways. I usually, just for consistency, I usually expand along the top row. Okay, there's a 0 in the top row, so that's actually going to simplify things quite a lot. So it's basically you cover up. You start up here and you go, okay, this is in the first column and the first row. So I cover up the first column and the first row, and I multiply this by the determinant of what's there. Then I move on to the next one. 3 is in the middle column. The middle column in the top row. So I cover up. multiply 3 by the determinant of what's left, and then I move on to the 0. Don't forget, there's a minus sign, so it goes positive, negative, positive, negative, positive, negative. Okay, so remember how to expand 2 by 2 matrices, or I guess determinants. You multiply here and here, and here and here, and you take the second away from the first. So this is going to be that times that, which is just there, minus that times that, which is there. That times that, minus that times that. And of course, this third term is just going to be 0. So that's nice and simple. Okay, now you've got to solve this equation on the bottom line. It's very tempting to think about expanding all the brackets, but don't. Okay? Don't do it unless you have to. You can see there's a common factor of 1 minus lambda. Okay? So I can use that and pull out a 1 minus lambda in this particular example. It won't work all the time, but it will work quite a few times in my experience. Okay, so I'm going to pull out that factor of 1 minus lambda. And then all I need to do is simplify this. Now this is going to be a quadratic in here, so that's not going to be too hard to sort of to factorize. So now if I expand the brackets, I'll get this. And thank goodness, that's going to simplify quite nicely. So my factors are going to be something like positive 4 and negative 3 for this particular term. So that's the first part. Now, they ask you to find the associated eigenvectors and hence express this equation in terms of its principal axes. You don't need the eigenvectors to do part I. Values, let's just write down the principal axes form of the equation. So here's our Q. I'm just going to define that as a function Q. That's given to us in B part I. And what we want to do is simplify Q under some new coordinate system. Now the important thing here is that for the matrix A, given at the start, you can write Q in this quadratic form, this X transpose AX, where X is a vector. Okay, so if we write X as the vector X, Y, Z, then this and this is the same for our A. So what does that mean? Well, it means that there is an orthonormal system of coordinates. Say, just think of them as a new set of coordinates, big X, big Y, and big Z, such that, and this is the important part, Q has the following form. Now the lambda 1, the lambda 2, and the lambda 3 are just the eigenvalues of A. Now you see how this is potentially much simpler than this mess up here? Okay, this could be a bunch of surfaces depending on the signs of the lambda 1, lambda 2, and lambda 3. But the thing is, it's much simpler than this thing up here. Okay, so our lambda 1, lambda 2, lambda 3, I've labelled them as lambda 1 equals 1, lambda 2 equals 3, and lambda 3 equals minus 4. Now you don't have to put them in that way, if you put, say, the 1 here and the 3 here, you'd still be correct. You'd still be correct, okay? So what kind of surface is this? Anyone know? Correct. So it's a paraboloid, one sheet. Which axis is it going to be wrapped around? There's y. Yeah, or I mean, I just look for the negative sign here. Okay, so you're absolutely correct. It is a one-sheet hyperboloid that's wrapped around the z-axis. Okay. So we've written down the principal axis form of this. Now we're asked to write out an orthogonal matrix P such that little x, little y, little z is just P times big X, big Y, big Z. So for that, we will need the eigenvectors. Okay, we will need the eigenvectors. Okay, again, you don't need to write all this down. So how do we construct an orthonormal matrix P? Well, first of all, what is an orthonormal matrix P? It's just one where the inverse is the transpose. So it's easy to calculate the inverse of an orthonormal matrix. Or orthonormal. Now, how do we do it? Well, let's construct the eigenvectors and normalize them. Okay, so let's denote the eigenvectors v sub I of A, normalize them, write them as a matrix in column form, and that'll be your orthonormal matrix of interest. Okay, so one other side comment is that since A is symmetric, the set of eigenvectors forms an orthonormal basis. So we can really, like the big X, big Y, and big Z axes are all going to be sort of a nice framework from which to work within. Okay. So here I'm going to put in the specific values of my lambda. So lambda equals 1. You just solve this particular vector equation, right? You want to solve for the vector v. So whatever the v here, we'll call that v sub 1. That'll be our eigenvector corresponding to lambda equals 1. So A was up here, so let's consider A minus lambda I for lambda equals 1. So it's basically just going to be this matrix here without the determinant signs with lambda equals 1. So if you write that down, we get this equation. And if I look carefully, I can see, all right, 3v2's got to equal 0. So I can immediately conclude that v2 equals 0. What else? Well, the bottom line only just tells us that v2 is also 0. It's the middle row that we're interested in. Now, I could write out the middle row, the equation for the middle row, but what I might do is just add the first row to the second row, and I'll get 3v1 equals v3. Okay? So that's pretty much all the information we've got. We know what v2 is, but v1 and v3 are arbitrary in the sense that there could be a lot of v1s and v3s that satisfy this bottom equation. So let's just pick a simple value, say for either v1 or v3. I've chosen v1 to be 1. So if v1's 1, v3 must be 3 times 1. And of course, v2 is 0. So that's my eigenvector, my first eigenvector. So that was pretty easy. We didn't really have to do any row reduction there. We could just kind of do it in our head. Okay, note that you can choose V1 here. Now, this answer here isn't unique. It could be any multiple of this as well. I could have chosen V1 to be 2. In that case, I'd get V3 equals 6, and I'd still be correct. Okay, so with eigenvectors, if you and your friend get a multiple of each other, you're still correct. Okay, so that's our first eigenvector. Let's move on to, say, the case lambda equals 3. So if lambda equals 3, we consider this equation here, and we want to solve for v. So writing it out again, I get the following. Now, it's not quite as simple as the previous case, because I can't just read off the answers. So I'm going to do a little bit of row reduction on this, just to simplify things. Now, I haven't done all the row reductions because I don't think they're really necessary. I'm just doing enough to solve the problem. So what I've done is that's already a 0. So I'm just going to make that a 0 just by multiplying some multiple by the first row and adding or subtracting it. In this case, this is the relationship here. And I can see these bottom two rows are a multiple of each other. So again, I'm going to get an infinite number of solutions. Let's say I write out the equation with the first row involved. That's going to give me 2v1 plus 3v2 equals 3v2. And let's choose this one. That's going to give me v2 equals minus 2v3. So now I just need to choose. I'm going to choose v3 to be 1. That'll give me v2. And once I have v2, I can then get v1. So that'll be my eigenvector. Okay, we're almost there. Two down, 1 to go. The case lambda equals minus 4. So again, we're going to solve this this equation with lambda equals minus 4 this time. So now it's just a case of writing it out again. I get that. You can see why I pre-prepared the slides. I don't think there'd be enough room on the board to do all this, or time either to write all this stuff out just from scratch. So if I look here, I can definitely get a relationship between v2 and v3 and v1 and v2. But I have chosen to just reduce it a little bit. It might not be necessary, but with this particular operation, I can see that the second row and the third row are a multiple of each other. And then all I'm really doing is I'm going to use this and this. So you don't really need to do that, I guess. So the first line gives the first row up here gives me 5v1 equals minus 3v2. The last row will give me v2 equals 5v3. So I'm going to choose v1 to be 1. That'll give me v2 equals 5. v3, and once I have v2, I can then just plug it in here to get v1. So they're my 3 eigenvectors. It was a lot of work, but we got there. Okay? It was a lot of work. It's easy to make a mistake. In fact, if you look hard, you can see a bit of liquid paper in here where I've made a mistake. Okay? It happens to us all, don't worry. Okay, so 3 eigenvectors. We want to normalize each of them and then write them as columns in a matrix. That's my orthonormal matrix P. So I haven't written out I haven't spent any time on the normalization. I've just sort of written it down. So the length of this vector is going to be root 10. The length of this vector's, of the v1 vector is going to be root 10. The length of v2 vector is going to be root 14, and the length of v3 is going to be root 35. So you divide by those lengths. Oh, a lot of calculations. So that is your orthonormal matrix P. The last thing they ask us to do, such that this is true. The last thing they ask us to do is deduce, part C, deduce from your results the shortest distance from the origin to the surface described in part B. So we talked about this a little before. This is the principal axis form of my equation. And we said, okay, it's a one-sheet hyperbola. Now, here I've drawn them in the big X, big Y, big Z plane, coordinate system. And in particular, it's a one-sheet hyperbola wrapped along the Z-axis. Now, let's look at this actual surface. The minimum distance to the origin is going to occur, because it's sort of curving in this way on all sides, it's going to occur in the XY plane. Okay? That's the smallest kind of, I guess the distance to the origin is going to be somewhere in there. The smallest, the point which is the closest to the origin. Now let's just draw that cross section. It's going to be an ellipse. So basically I just cover up the Z and I've got an ellipse, right? That's it there. If I rearrange that, put it in the standard form, I can draw the ellipse in the XY plane. Now, where's the closest point on that ellipse to the origin? Well, it's either there or there. Well, it's the same distance. So from this little picture, you can see that the minimum distance to the origin occurs at this point and this point, and it is actual just that length and that length. Okay, can you see why I pre-prepared those slides now? 93 is another application of eigenvalues and eigenvectors. Okay, you can see that we've got a system of differential equations here. So think of this as like a vector differential equation. And we're asked to use eigenvalue methods to find the general solution to the following system. Okay, let's have a look. Oops. Okay, so firstly, notice all the coefficients are constants. And you can actually write this system as a matrix times a vector. So let's have a look. Whoops. I can actually write the right-hand side of my differential equation as involving matrix and vector multiplication. So the x dash, the y dash, and the z dash mean dx dt, dy dt, dz dt. Okay? So here x, y, and z are all functions of t, the independent variable t. Okay, so in basic notation, that can be written as that. Now, A is not a symmetric matrix in this case, but doesn't matter, we can still solve it, no problem. You might have seen this in first year, so this is just 3, not a negative 3. In first year, actually I think in algebra, but let's actually go through and have a look at it. One of the important points of our solution is the idea that the solution to this linear system with constant coefficients. Just think of this matrix as a constant matrix. It's just got numbers here, not functions. What we do is the solution's built or constructed from the eigenvalues and the eigenvectors of the matrix A. So let's go through and calculate them. Calculate the eigenvalues first. Okay, again, be careful. We look at the following determinant equation. And essentially we want to find the lambda that satisfy this equation. So let's write it out. Look at the determinant and expand along the top line. Again, I just do that out of habit. Okay? You don't necessarily have to do it. So I cover up, so let's go to this term first. Cover up the row and the column and multiply by the determinant of what's left. That's there. Middle column, top row, look at the determinant of what's left and put a minus sign there. And then move on to this one, cover up, and multiply that one by the determinant of what's left. Okay. So now let's expand those 2 by 2 matrices. Remember, it's just, say for the first one, that times that minus that times that. That times that minus that times that, and etc. Just this sort of cross multiplication. So if I expand that out, I'll get some big mess like that. Now, unfortunately, I can't see any common factors in there just by pulling out, you know, say a 1 minus lambda or a 7 minus lambda. So I couldn't see a way of factorising this economically. So now I'm going to break the rule that I said to you before. I am going to expand it. Okay, but don't worry, I'll leave you to do that. This is what you get. If you can see a nice factorisation, let me know, because I couldn't see one. All right, so we get this. We want to solve this equals 0, so I can basically just change the signs and make that first term a little simpler. So I've got a cubic type a polynomial, right? How would I factorise this cubic? Anyone remember? Anyone? The factor theorem? Yeah. Well, the factor theorem's a little hit and miss. The factor theorem says, okay, just by trial and error, find one of the roots of this polynomial. Can anyone see one straight away? 1? Yeah. Minus 1. You can experiment a little bit, okay? Now, okay, let's say I've come up with one particular value for my lambda. If I plug in minus 1, lambda equals minus 1, these will all add up to negative 24, and they'll cancel with that, and the sum will be 0. So the factor theorem says that lambda minus 1 is just this, is a factor. So what you could do now is do long division. But can anyone see a smarter way than moving to long division? Well, look at this 24. Look at the factors of 24. There's quite a few, right? But one good way is to look at the factors of 24 and then test them. So think of what factors are 24. Yeah, 8 and 3. Right? If you test 8 and 3, 8 and 3 actually works. So 3 solves is a 0, 8's a 0, so these must be factors. Pretty sneaky, huh? So think about... Yes, I'm not, yes, okay. But can you see how I've saved a little bit of time here just by looking at that constant? Okay? Of course, you can go through and do long division. If you can divide fast, there's no problem. You don't even have to do that. But students, in my experience, students are resistant to long division, or they don't really, they don't hardly ever use it. So they've forgotten it, Anyway, I'll leave that with you to choose the method that you like the best. Okay, so these are our eigenvalues. So let's calculate the eigenvectors associated with each of those eigenvalues. So, again, we solve this vector equation for the case lambda equals -1. We want to solve for the vector v. That'll be an eigenvector. So if I write that out, I'll get something like this. I can feel a bit of row reduction coming on. So what I've done, over here, I have switched out row 1 and row 3 just to get a 1 here. Then I'm going to take multiples of the first row away from the second and third row. All right, so I want to make that 3 a 0 and that 8 a 0. So let's take 3 times the first row away from the second row, and 8 times the first row away from the third row. Now, just a little suggestion, if you are doing row reduction, make sure you write down your operations clearly. Okay? Number one, to keep you on top of things, but also for the person who's marking it. Okay? They want to see the operations. Look, just by reading your operations, the marker can kind of some way get inside your head. Okay? Even if you made a little mistake somewhere here, if that's there, then you should get some part marks. Okay, well, you can see the second row is a multiple of the third row. So we're going to get a row of zeros down the bottom. I know that V2 and I've got this row to give me some information about V2 and V3. So V2 and V3 are going to have opposite signs. And this top row I can just write out like this. Now, if V2 and V3 is 0 and I've got 3 times V2 plus V3 here, I can just replace this with a 0 just by putting that in, and I get V1 equals 0 straight away. How nice is that? So putting this into here gives me V1 equals 0. Now all I'm going to do is just choose either V2 or V3. I'm going to choose V3 to be 1, so V2 equals -1. So that's my eigenvector. V0, V1, V2, V3. So that's the first case, our first eigenvalue and our first eigenvector. We've got 2 more to go. So, anyone still going up here? Okay, all right. So I might take this away. So let's solve for the case lambda equals 3. Again, we solve this equation for v, and lambda equals 3, so that's what you get. Now, again, this looks slightly more complicated. So what I've done is I've changed that 4 to a 1 just by swapping rows 3 and row 1. So we get a 1 up there. And then what I'm going to do is take away multiples of row 1 from the second and the third row. So I get 2 zeros here and here just by doing that, and you can see this row is the same as this row. So again, we're going to have a row of zeros down the bottom. So in this one, it'll be row 3 goes to row 3 minus row 2. Okay, well, up the top, I've got some information. Down in the middle, I've got some information. I know V1 equals negative 4 on 11 V3, and V2, V11 V2 is going to be 5 V3. So I've got those. Okay, so let's see if we can hunt around and find the V1, V2, V3. Well, if I choose V3 to be minus 11, then I get whole numbers for V1 and V2, so I can set up my eigenvector this way. Now, you could choose V3 to be 1, but you're going to get nasty fractions in here if you don't make a reasonable choice. If you want all whole numbers here, okay? But it's easier to work with whole numbers rather than fractions. Okay, that's the second situation. Let's move on to the last eigenvector. The last eigenvector. So lambda equals 8, solve the same type of equation, just with lambda replaced with 8. And you'll get this case here. And again, you can't read off too much information from this immediately. So I've done a little bit of row reduction. And here's what I've come up with. So I'm moving a little quicker now because we are running out of time. Okay, again, you don't have to write down the whole thing. My V3 is just here. Okay, so let's summarize what we've got so far. We've got the eigenvalues. We've got the corresponding eigenvectors. What do we do with them? Anyone remember? How do they relate to the solution of ODE, the system? Anyone remember? Well, let me just refresh your memories. Whoops, sorry. Couple of important points. Since our eigenvalues are all distinct, there's no repeated, they're all not equal to each other, right? There's no sort of doubles or anything. And since our ODE is linear, the general solution is just a linear combination of these particular vectors. So this vector, this vector, this vector. So this is the eigenvector associated with this eigenvalue. Same with this one, same with this one. Okay? C1, C2, and C3 are just constants. They're just arbitrary. We don't know what they are. We can't calculate them, but to cover the most general case, we need to put these constants in. So let's write down our eigenvalues, our corresponding eigenvectors, and then we'll have our solution.